Hello, it is Mrs. Avila here, and I am reporting from my kids' playroom. If any tiny people walk in during this presentation, I'll have them say hi, and otherwise we can continue on our way. All right, so we are going to be talking today about 11.3, independent and dependent events. And what I'm going to do is I'm going to go ahead and I'm going to see if I can close out this window down here so that you're not distracted by anything happening in the background here while we do our lesson. All right, so independent and dependent events. Let's clarify what it means to be independent first, and we can go from there. All right. So there we go. Independent events is if the occurrence of one event does not affect the probability of another. If you know two events are independent of each other and you want to know the probability of both things occurring, you can simply multiply their probabilities. So if I know that one thing happening doesn't in any way affect the chances of the second thing occurring, those would be known as independent. So let's look at a scenario here. Example 1, find the probability of independent events. So let's say we're talking about a spinner, like a game spinner. Maybe you've seen one in Twister or Life. So the game Life, not just Life itself. But you are playing with a game spinner, and you want to know the probability of spinning a 4 and then a 4 again on the second spin. So first of all, we need to double check, does it make sense that they're independent? What I spin on the first try doesn't in any way restrict what I can get on the second one. So I'm going to go ahead and say that it makes sense that these are, in fact, independent. So to find the probability of those two things happening, I first need to know, well, what's the chance of getting a 4 on the first spin? Well, getting a 4 on the first spin, it looks like there's 3 of them. So I'm going to say 3 out of 8. And then the chance of the second thing happening is getting another 4. That would also be 3 out of 8. So the chance of both things happening would be 9 out of 64, also known as, I could say, 0.1406. I could also say that that is 14.06%. Okay. B says, what's the chance of spinning a red, then a green, and then a red? Okay, well, does it make sense they're independent? I'm going to say yes in this case for the exact same reason as we mentioned in A. The spins don't affect each other. So I want to know the probability of getting a red and then getting a green and then getting another red. Well, the chance of getting a red looks like there are 2 out of 8. I could also say just 1/4 of them are red. Then there's 3 out of 8 that are green, and then the chance of the last one being red again is going to be 1/4. So if I multiply those out, I'm going to get 3 out of 128, which would be 0.023. That should be 4. There we go. All right. Go ahead and try these two problems. For the record, when it talks about rolling a number cube, it's just talking about rolling a regular 6-sided die that you might have used in like a game. All right, so we want to know the probability of rolling a 6 on a die and then another 6. Well, rolling one doesn't affect the outcome of the other, so I'm going to say they're independent. So what's the chance of rolling a 6 on the first number cube? That's a 1/6 chance. And then it's still a 1/6 chance of rolling the second one. So I'm going to say 1 out of 36, which is 0.0278. B says, what's the chance of tossing a head, then a tail? When we say tossing a coin, we're talking about like a fair 2-sided coin. So the chance of getting a heads on the first one, I would say, is 1/2. The chance of getting a heads on the second one is 1/2, and then getting a tails on the third one is 1/2 as well. I'm going to go ahead and multiply those since they don't affect each other. They're independent. I'm going to get 1/8, or I can say 0.125. All right, so to find probability of independent events, you can simply multiply their chances of occurring and get their total probability. Dependent is a little bit different, though. Dependent means that if the occurrence of one event affects the chance of another event, What that means is you ultimately have to adjust the chance of the second thing occurring based off of the first one happening. So here's an example. Suppose that there are 2 lemons and 1 lime in a bag. If you pull out 2 pieces of fruit, the probabilities change depending on the outcome of the first. So if I pull out a lemon on the first draw, now my chances on the second draw of getting a lime versus a lemon are different because the bag has changed. So what can we do to find that probability? Well, if you have dependent events and you want to know the chance of them both occurring, you can still simply multiply them. But the tricky part is you have to adjust the chance of the second event occurring based off of the first. That involves something called conditional probability. Conditional probability is just the probability of a given event. So a probability of event, let's say B, given that something like A, we can call it, has already occurred. A perfect example of conditional probability, if anyone is familiar with card games, is blackjack. The likelihood of you winning blackjack or not busting in any given round of blackjack is dependent on the cards that have already been removed from the deck. All right, so back to this lemons and lime example. Let's say we want to know the probability the second piece of fruit is a lime, assuming that you selected a lemon first. So I'm going to say the probability of getting a lime given that I got a lemon on the first draw. So I need to ask myself, well, what's the chance that I got a lemon on the first draw? Well, it looks like originally there was a 2/3 chance on the very first draw to get a lemon. Now I want to know what's the chance of a lime happening as a result. My chance of getting a lime on the next one, I would say, is 1/2. So I could say 2 out of 6, or I could say 1/3. If you want to see kind of the sequence of this calculation, it's like saying the probability of the lemon times the probability of the lime with the lemon already happening, already being pulled out. Okay, so that's what those probabilities are. All right, so let's look at a couple examples, and I'm going to show you 2 ways that we can do them. Now, if it's a scenario involving something that you could physically imagine, like rolling dice or flipping coins, sometimes it helps to draw that out. For this example, I'm going to be talking about rolling a red and a blue die, and so I drew out a little, it's called a sample space, if you want to think of it as listing out all the combinations. And this says, what's the probability the red cube shows a 1 and the sum is less than 4? So I can do this 2 ways. I can think of it as the formula method versus the kind of do it all at once method. This is going to completely depend on your preference and which one makes more sense to you, but hopefully you can follow along with both and make that decision. So option 1, let's use the formula. If I want to know the probability of the red cube showing a 1 and the sum being less than 4, I need to break this down. I need to say, okay, what's the probability of the first thing happening? So the red cube showing a 1. And I'm going to multiply that by the probability that the sum is less than 4, assuming that the red cube already had a 1 on it. So what's the chance the red cube just has a 1? That would be my entire top row. So I could say 6 out of the 36 outcomes have a red cube with a 1. Now the second part, that red cube having a 1 is my given, meaning I'm only looking out of those 6 outcomes. How many of them have a sum less than 4? It would be these first 2. So when I go ahead and I multiply that out, I'm going to get 12 out of 216, which is 0.0556. I could have done this entire problem based off of just looking at the 2 characteristics all at once. Let's say I wanted to think about it out of all 36 outcomes at the very beginning. Out of those 36, I want to know how many of them have the red cube showing a 1 and the sum is less than 4. These are the only 2 outcomes out of all 36 that have both of those characteristics. And what do you know? That still gives me 0.0556 as my probability. Let's look at another one. Again, I'll show you both methods so you can try them on your own in a minute. Same 2 number cubes being rolled, 1 red, 1 blue. What's the probability that the blue shows a multiple of 3 and the sum is 8? So I'm going to try and find the probability that the blue is a multiple of 3, and then I'm going to multiply that by the probability that I get a sum of 8 given that blue multiple of 3 already occurred. So the chance that the blue is a multiple of 3, that would be this column and this column. So I would say 12 out of the 36 have a blue multiple of 3. Now, out of all those blues with a multiple of 3, so out of those 12 that I just narrowed it down to, how many of them also have a, let's see, how many of them also have, what was it, a sum of 8. So a sum of 8, that would be this 5 and 3 and the 2 and the 6. So I'd say 2. And if I multiply that, I'm going to get 0.0556 again. Okay. All right, and again, we could try this all at once. I could go back to the drawing board. Let me erase what I have, and I could say out of all 36 outcomes, how many of the 36 have the blue with a multiple of 3 and the sum being 8? It would still just be those 2, which again, by the way, it just so happened that A and B had the same final answer, but it wasn't on purpose. All right. So once you try a couple, I want you to try and wrap your head around whether these two things are independent or dependent, and then you can try and find their probability either of the two methods. For the record, on your paper it says there's a red and a black cube. You're welcome to just change that to a red and a blue cube if you want to use the picture. Alrighty, now that I know every single one of you paused the video and tried those on your own, let's try and figure out why these are independent. Or sorry, why these are not independent, why they are dependent. So I like to think of it as, does knowing the first thing happen, does that narrow down the chances of the second thing? So if I look at this and I want to know the red cube shows a number greater than 4, does knowing that in any way narrow down my choices in regards to the sum being greater than 9? And if I know I'm only looking at red cubes greater than 4, if I'm only looking at these bottom 2 rows, that immediately eliminates this outcome over here as being one of my possible choices for having a sum greater than 9. So the fact that I would say knowing that the red is greater than 4, I can say changes the chance, or you could say probability, of getting a sum greater than 9. That's why they are not independent. Okay, so now let's find that probability. So what's the probability of, let's say, the first thing? Let's say, what was it, a red greater than 4, and multiply that by the probability of getting a sum greater than 9 given that we had a red greater than 4. Chance of the red being greater than 4, I'm going to go ahead and say out of the 36, there were 12, all the 5s and 6s. And then out of those, the given that it was greater than 4, so out of those 12, how many of them also happen to have a sum greater than 9? That would be 5 and 6, 6 and 6, 5, 5, 6, 5. It would be those 5 options right there. So I multiply that out, and I'm going to get 0.1389. Again, I could have, right from the beginning, just looked at it all at once, and I could have asked myself, out of the 36 combinations, how many of them have both a red greater than 4 and a sum greater than 9? I would still be looking at these 5 outcomes here. It would be 5 out of 36. And that would also give me 0.1389. All right, so let's wrap it up. Let's look at not only how can we calculate independent and dependent events, but how can we tell whether they're independent or dependent? 2 cards are drawn from a deck of 52. Determine whether the events are independent or dependent and find their probability. So A says selecting 2 aces from the first card, let's say if replaced. or when they're replaced. For those of you that are not familiar with the standard deck of cards, they're used a lot for probability problems. So please refer back to our review section in the agenda. We have a sample space of a deck of cards that you could use as a point of reference. So what's the chance of getting 2 aces in a row when it's replaced? Well, I'm going to start by picking out of 52 cards, 4 of which are aces. If I put that card back before I select my next one, I'm still going to be picking out of 52, and there still would be 4 aces remaining. So I'd get 4 out of 52 times 4 out of 52. That's going to give me 1 over 169, which is 0.0059. Basically, not likely. All right, B says selecting a face card and then a 7 when it's not replaced. So this would be dependent. So the probability of getting a face card on the first pull, well, there are 12 total face cards, 3 of each suit, and there's 4 suits. And if I'm not putting that face card back when I go to pick my next card, it means there's only 51 cards remaining. I'm picking a 7 next, and all 4 7s still should be in the deck. So that would get me 48 out of 2,652, which is 0.0181. All right. Go ahead and try this last problem, and then you can check your answers. Okay, and so this last problem, it talks about a bag containing containing beads, black, white, and red. And we want to know if they're independent or dependent. So A says selecting a white bead. We are then replacing it. So that tells me that this is going to be independent. And then getting a red bead. So the chance of first getting a white bead out of 10 beads, 3 of which it said are white. I put it back, so out of my second draw, there's still 10 beads, and I want a red one this time, and 5 of them were red. So that's going to get me 0.15. B is the chance of selecting a white bead, not replacing it, so this is going to tell me that this is dependent. So my first draw, out of my 10 beads, I want a white bead, which is still 3 out of 10. But now on my second draw, I only have 9 beads left in the bag. I want to know the chance of the next one being red. There still should be all 5 reds, but there's only 9 total in the bag. So that's going to get me 0.1667. And last but not least, selecting 3 non-red beads without replacement. So not putting them back means that they're going to be dependent. My first draw, I'm picking out of 10, 5 of which are red, which means 5 are non-red. My second draw, there's only 9 beads left. There should only be 4 non-reds left, assuming that I pulled one of the non-reds out on the first draw. My last draw, there's only 8 beads left, and there should only be 3 non-reds left. That's going to give me 0.0833. All right, hope that helps clarify the difference between independent and dependent events. Remember, you can always multiply. The question is, do you need to narrow down the odds of the second event if the first one affected it? Let us know if you have any questions. Feel free to shoot them my way, or Jeffrey's or Han as well, and we look forward to hearing from you.